Greetings, class. Have you ever wondered why elements like potassium completely break the rules of how electrons are supposed to behave? It's kind of like they're playing a cosmic game of hide and seek in these fuzzy probability clouds. Well, today we will study the fundamentals of atomic orbitals and electronic configurations.
This is a scientific mystery that's literally puzzled students for generations. But we're going to unlock that mystery right now. We're going to decode the very architecture of the universe, literally atom by atom.
All right, before we can even think about building an atom, we need to figure out exactly where its building blocks actually live. So, the absolute foundation of everything we're covering in this explainer rests on this one single definition. An atomic orbital is a region of space around the nucleus of an atom that can be occupied by 1 or 2 electrons. That's it. Not 3, not 4, a maximum of 2. Lock that concept right into your mind, okay?
Okay, let's dive into this. Section 1. Quantum subshells and energy. Understanding principal shells and sublevels.
So, I want you to think of an atom like a massive, invisible apartment building. The principal quantum shells, well, those are the floors of your building. The first floor is pretty small, but as you go up, the floors get bigger and they split into different types of apartments. We call these subshells, and these subshells are named S, P, D, and, for the really massive atoms with over 57 electrons, F. Now, just like a real apartment has a strict occupancy limit, so do subshells. The S apartment can only hold 2 electrons. The P apartment can hold 6, and the D apartment is basically a giant penthouse that holds up to 10. And naturally, the energy, think of it like the rent, always increases as you move from S up to P and then to D.
Let's do the capacity math real quick. Floor 1, or n equals 1, just has an S subshell, so it totally maxes out at 2 electrons. Floor 2 gets an S and a P, bringing its maximum to 8. Floor 3 adds that D subshell into the mix, bumping its total capacity up to 18 electrons. Now, you might be sitting there wondering, who on Earth came up with the letters S, P, and D? Well, when early scientists shot high-speed electrons at low-pressure gas, they used these devices called spectroscopes to look at the colored lines that popped out. And they literally described these spectral lines as sharp, principal, and diffuse. I know, right? It's a rather uncreative naming convention, but those historic labels stuck. And that is exactly why we use S, P, and D today.
Here are the core details regarding this topic. Review them intently for their deemed crucial for your finals.
Moving right along to Section 2. Atomic orbitals and shapes. The geometry of electron clouds.
Okay, bring your mind back to our fundamental definition. A single orbital holds exactly 2 electrons. So if an S subshell holds 2 electrons total, well, it has exactly 1 orbital. The P subshell holds 6, so it needs 3 orbitals. And the D subshell holds 10, meaning it requires 5 orbitals. Makes sense, right? Now, every S orbital is a perfect symmetrical sphere. A 1s orbital is a small sphere, while a 2s orbital is basically just a larger version of that same sphere. Its electrons possess higher energy, sure, but that spherical geometric shape, it remains exactly the same. And this brilliantly illustrates exactly how these probability clouds scale up.
The p orbitals, though, look vastly different. They resemble an hourglass, or maybe a dumbbell, with 2 lobes arranged at right angles along the x, y, and z axis. And all 3 of these have identical energy. We actually owe this whole understanding to Louis de Broglie. Back in 1925, he famously suggested that electrons behaved like waves, which directly gave us this modern concept of electron probability clouds. Now the d orbitals, they get really wild. There's one called the DZ2 orbital that looks exactly like a p orbital wearing a cosmic donut right around its middle. You don't actually need to draw these complex d orbital shapes for AS level, but hey, consider this your fair warning. When you hit A-level transition metals, you will absolutely need to know these weird and wonderful shapes for sure.
These are the vital facts linked to this section. Study them thoroughly as they are vital for examination point of view.
Section 3. Filling the shells and orbitals, the rules of the game. So the absolute golden rule of chemistry is stability. And stability means finding the lowest energy state possible. Because of this, electrons always fill the lowest energy subshells first. We start right at the bottom. 1s fills first, then 2s, then the 3 2p orbitals, then up to 3s, and then 3p. It seems like a perfectly logical, predictable sequence, right? But take a close look at step 6. The 4s subshell is filled before the 3d subshell. Wait, what? Why on earth would the 4th floor get filled up before the 3rd floor is even finished? Well, here's the answer. So the crucial point is that the filling order completely stops following a regular pattern after the element argon. After argon, where the 3p is full, the subshell energy levels physically overlap. Even though 4s is technically in the fourth principal shell, it actually sits at a slightly lower energy level than the 3d subshell. Because electrons are, well, inherently lazy and always seek the lowest possible energy, the very next electron goes right into the 4s. This brilliant little twist of quantum mechanics explains exactly why potassium's outer electron enters 4s instead of 3d. It actually isn't until element 21, scandium, that an electron finally goes back to start filling up that 3d subshell.
Which brings us to section 4, representing electronic configurations, notation, and the first 18 elements.
This notation is essentially a detailed address system for electrons. Let's break down the syntax of 1s1, which is hydrogen. The leading number, 1, is the principal quantum number. That's the floor. The central letter, S, is the subshell, the apartment type. And the superscript number, that little 1 at the end, shows the exact number of electrons living in that specific apartment. So helium has 2 electrons, filling the first orbital completely. We write that formally as 1s2. Lithium has 3 electrons. Since the 1s is completely full, that third electron is forced up to the next highest subshell. So we write lithium as 1s2, 2s1. You basically just add them one by one, constantly following that energy ladder.
Let's move to and see how this builds. If you look at the sequence here, there is a perfect, logical progression of electrons from hydrogen all the way down to argon. They predictably fill the 1s, then 2s, then 2p, then 3s, and finally the 3p subshell. It is a beautiful, uninterrupted sequence, well, right up until we hit element 19.
Section 5, advanced filling and exceptions, the rule breakers. Okay, first, a really quick tip. Instead of writing out a massive, tedious string of numbers for larger elements, scientists use a shorthand method called a noble gas core. So putting argon in brackets, R, stands in perfectly for those first 18 electrons. But listen to me carefully here. Do not rely entirely on this shorthand if your exam strictly asks for the full unabbreviated notation. Always, always read the question. Now, moving on. After calcium fills the 4s subshell, the 3d subshell finally starts getting its electrons. Scandium kicks off this trend with an ending configuration of 3d1 4s2. This whole block fills up steadily until we reach zinc, which completely fills the d subshell, ending in 3d10 4s2.
But tucked right inside that block lie our 2 notorious troublemakers. Just look at chromium and copper. Based on literally everything we just learned, chromium should be 3d44s2, but it's not. It is actually 3d54s1. And copper should be 3d94s2, but it actually forces itself into 3d104s1. No way, right? They completely break the pattern.
You have got to explicitly memorize these 2 rebellious exceptions for your exam. Seriously, chromium literally steals an electron from the 4s to make its 3d subshell exactly half full, 3d5, 4s1. Copper steals an electron from the 4s to make its 3d subshell completely full, 3d10, 4s1. Burn those 2 specific configurations right into your memory. Now, once that drama is over and zinc finishes the 3d block, normalcy finally resumes. The next highest energy level is 4p, so elements from gallium to krypton progressively fill up the 4p subshell without any further rule breaking.
Section 6, high-yield summary, core takeaways. Now, what's really interesting about this slide is how it ties everything together in one neat package. All right, let's lock this in before we finish. Orbitals are 3D regions holding a maximum of 2 electrons. Subshells, S, P, D, and F, have distinct shapes ranging from spheres to complex dumbbells and rings. Some shell capacities are strictly fixed. S is 2, P is 6, D is 10. Remember, electrons are lazy. They absolutely must populate the lowest available energy levels first to ensure stability. Because of a crucial energy overlap after argon, the 4s subshell fills before the 3d subshell. Configuration notation precisely maps out the principal shell, the subshell, and the total electron count. And finally, chromium and copper remain your critical, must-know exceptions to the standard filling pattern.
You know, you've done a fantastic job navigating the complex architecture of the atom with me today. But before I let you go, I want to leave you with a bit of a puzzle for your next study session.
If electrons naturally seek the lowest possible energy state, why do you think the specific exceptional arrangements of 3d5 4s1 for chromium and 3d10 4s1 for copper ultimately represent a more stable energy state than what the standard rules predict? What is it about a perfectly half-full or completely full d subshell that the universe just seems to prefer? Ponder that, chemical mystery class, and I will see you in the next explainer.
Essential terms related to topic are displayed organized according to different exam boards. These keywords need careful attention during revision because they are crucial and should never be ignored. Besides this, past paper analysis is provided for each board and paper type. Make sure to focus on it as it will significantly support your preparation. Also aim to understand the usage and meaning of each keyword rather than memorizing them separately. Continuous practice with these terms in past paper question will improve your accuracy and overall performance.
Please subscribe our channel to get more educational videos. Thank you.